Okay.
So I created your exams. I put some grades on it. It's kind of hard to assign grades in a class like this where all of you are, hard working and doing such a hard course. If you feel the grades are too low, just let me know. I'll increase the grades. So that is what I feel I've done. I've given you a fairly honest grade. Okay. But on the other hand, if the grade is too low for you, I'm sort of open to I'm not so fixed on giving you these grades. Given sort of I feel your work on homework is almost outweighs the exams. So burn yourselves out on homework. Really work hard on homework. That's to me that's more important. Okay. Okay, so today we're going to be talking about tempered distributions. So William, I was just saying that, so I put grades on these exams, but if you guys feel the grades are too low, I'm sort of half joking here, but I'm half serious. I'm sort of willing to, just raise your grades. Okay. So we're talking about tempered distributions, right? This is a special class, an important class of distributions, mainly for its interaction with the Fourier transform. Okay, so let's just quickly recall what's going on. So tempered distributions. Why do I feel like I'm shorter? Okay. First off, we have for infinity functions, we have these norms, right? So we have defined these norms, these sub n norms, where these n are natural numbers. We have these funny norms. So these norms are defined to be the supremum over all x of the x beta times d alpha x b x. And alpha and beta are multi-indices of index less than n. In other words, we're taking the bound, right? We're taking the L infinity norm, right, of all derivatives and all derivatives of the function and all multiples of those derivatives of the function and those derivatives by monomials, where the derivatives and the monomials are allowed to be of degree less than n. Okay. Okay. And so you take the supremum of that thing, right? And that's called the n norm. Okay. So there's this family, there's this infinite family of norms. Okay, defined on C infinity, and as you recall, the Schwartz class S Schwartz class is all everybody in C infinity such that this thing is finite for all n. Right. Schwartz class means that for your function and all its derivatives, if you multiply them by polynomials, then it's still finite, right? But those guys are still bounded functions. In other words, the function and all its derivatives are rapidly decreasing, right? Even if you multiply them by a polynomial, then it's finite, right? At least that it's bounded. Okay, so that's the Schwartz class. And then we have a couple more notions. As usual, we're going to avoid talking about the topology and just talk about continuity, the convergence that we'll talk about instead of convergence. So we assume phi sub k and you have phi in the Schwartz class. We say phi sub k converges to phi in the Schwartz class if phi sub k minus phi goes to 0 for all n. So the limit as k goes to infinity, this thing is 0 for all n. So convergence in the Schwartz class means that you have convergence with respect to every norm. Okay. With respect to every one of these norms.
But there's no uniformity.
There's no uniformity required. Okay. So yeah. So that's what we mean by convergence, and we're going to use that to define what it means to be tempered. Recall, if f is a linear functional on S, if whenever phi sub k converges to phi in S, we have f pk converges to f of phi, as numbers. Then we say f is an S star, that is f is a tempered distribution. Okay. In other words, whenever f is continuous, whenever f is continuous with respect to the convergence in S, basically you're saying whenever it's a continuous linear functional on S. Whenever it's a continuous linear functional, what does it mean to be continuous? That you preserve that you interact well with convergence. That you can commute with convergence. Okay, so whenever that happens, we say that you're a tempered distribution. So translating backwards, right, it says that this has the property that, these guys have the property that whenever this converges to, whenever phi sub k converges to phi with respect to every norm, right, with respect to every one of these norms, only then will f of phi sub k converge to f of phi. I mean, not only then, but in that case, f of phi sub k converges to f. So whenever you have convergence with respect to all the norms, definition of the temporary distribution. Next, we'll talk about properties. Temporary distributions. Okay. So the next proposition sort of tempers the previous statement. Right? Let me say that. So if f is a temporary distribution, then in fact there exists some n naught such that constant c such that f of phi is less than or equal to c phi times the n naught times the n naught for all phi n's. In particular, what does that say? That says that if you have convergence with respect to the n naught norm, well then, these numbers are going to converge. So there is a single norm. As long as you have convergence. Previously, we were saying that continuity means that if you have convergence with respect to all the norms, then you're going to have convergence of the numbers. But here we're saying that for a single, if you're looking at a fixed temporary distribution, well then, for that guy, you're guaranteed to have one norm that controls its behavior. Okay. So convergence with respect to that one norm ensures convergence of the couplets. So you are continuous with respect to that one norm. Unfortunately, this doesn't happen. It's only for that one. It's only for that one. Okay. So proof is by contradiction. Okay. You say, well, suppose there is. That doesn't happen. Suppose not. Then, for each n, you can find some C's of n in S such that C's of n's nth norm, the nth norm of C's of n is 1, and f of C's of n's n norm, whoops, excuse me, just the size of that, is bigger than n times that's just one. Okay, so well, in that case, take phi sub n to be 1 over root n times c sub n, and you see that you reach some sort of contradiction because say, well, look, so observe. For each fixed n, if little n is bigger than that, then the big N norm of phi sub n is going to be controlled by the little n norm of phi sub n, because you're taking the supremum over more terms. And so it's just going to get bigger. But what's this? Right? This is this equals 1 over. I mean, this is the piece of n. This is this, of course, which is 1 over root n. Right, so the point is that as n goes to infinity, each of these guys goes to 0. Right. Each of these guys goes to 0. So you're converging, that is, we have these piece of n's go to 0 in short space, in short space convergence. Here, it's okay. Anyone confused? Okay, so that means that, okay, well, those guys are going to 0, but if you look at the observation number 2, if you look at f of phi sub n, f of phi sub n is, of course, 1 over root n f of psi sub n. Right? But f sub psi sub n is bigger than n, right? So that's bigger than this is bigger than the square root of n. Right? This is one. Why did I invent this? Anyway. Okay. And so what's the point? These guys are going to 0, right? But this is infinity. So that's not right? Because you've got guys converging to 0, but they're outputs, but f on them is going to infinity. Okay, so that's the contradiction. So that's the first observation about these about tempered distributions. That there's a single norm for each one. There's a single norm that controls it. Okay. Okay. Second observation. Any compactly supported distribution f, right? So this is an old-fashioned distribution, right? So it's a linear functional on B, right? The compactly supported smooth functions as a extension to a tempered distribution. On S. So the book phrases this, that any compactly sorted distribution is a tempered distribution. But to be more precise, I think it should be phrased like this. You can extend it to a tempered distribution in a straightforward, but not necessarily, not unique way. So what you do is you say, well, look, let K be the support of F. Right? So K is some compact, K is a compact set. People usually use K for compact sets. I don't know why. Compact? Compact. So, and then to extend it, you sort of do the obvious thing. You say, well, I'm going to let phi be a C infinity function, compactly supported C infinity function. Let it be a compactly supported C infinity function, such that C is 1 on some open neighborhood. Open neighborhood. Okay. Let's see if your compact set. You have some open neighborhood. You have some open neighborhood around it, right? You let it be 1 there, and K itself is compactly supported, so it's basically like a bump function, right? It's going to be 1 here, and then it's going to decay and it becomes 0 outside of its own compact set, right? Okay, and then you sort of define f twiddle in the obvious way. Define f twiddle, right? By f twiddle of phi is f of phi times c. F and s. Oops, for phi and s. Right. You just consider, right? You basically, chop your function down to here, and then consider it. Let f act on it. So then, a twiddle equals f on d. So it is an extension. So it's an obvious extension of f. The only thing that you have to check is that is this thing that we created a tempered distribution, right? Is it tempered? Right. So, well, if p sub n goes to 0 in S, well, what does that imply? That implies that in particular that the L infinity norms of all the derivatives go to 0, right? So the each d alpha x dn, as n goes equals 0 uniformly, w.r.t. So that implies that these guys go to 0 uniformly on E. Right. And right, so and which implies that which implies that these guys go to 0 on D. Let's is this making sense? Remember, what we're trying to do. We're trying to show that if this goes to 0 in S, then we want to show that f twiddle of these guys we define them as f of c phi n. Right? Okay, so we're hoping that these guys go to 0. Right? Well, if we can show that these guys go to 0 in D, right? Remember, this was your old-fashioned distribution, right? Which means that it's continuous with respect to the D convergence, right? The old-fashioned distributions are continuous with respect to the D convergence. Now you have to remember what the D convergence was. The D convergence means that you and all your derivatives converge uniformly and are supported on the same compact set. Well, we're good. Everybody's supported on the same compact set because they're all multiplied by psi. And psi was supported on its own compact set, which included an open set, which included the compact set. This is the support of psi. This is the original support of the distribution. Okay. So all these guys are supported. All these guys are supported in support of C, right, which is compact. Right? Okay. And then we have the uniform convergence of their derivatives, and so we actually do that. We actually do have that we have convergence in D. Convergence in D ensures that f goes to 0. F of these guys goes to 0. Go to 0. There it is.
Where is this picture?
This picture is this line.
Sorry, I mean, what space is that in? Because I thought that K and like the support of F was distributions.
Yeah.
But the support of C.
No. Remember, how you figure out the support of the distribution is you look at the functions that it. You look at the functions that it is. You look at the support of the functions that it doesn't see. Right. And it's so remember, how was it phrased? Gosh. Does anyone remember exactly how to say this? The support of the distribution is the no?
It's the complement of the largest open set where distribution vanishes.
Right. So you look at the place where the distribution vanishes, right? Right, which is to say the sorry,
For all test functions, if you look at this for all test functions, and if f of the test function is equal to 0, you consider the support of these functions.
right.
And that's what functions.
Right. So you consider the support of those functions, right? And you say that's where the thing vanishes.
Okay.
And then you take the complement of that. That's still going to be an RD. That's going to be an RD, right? And so this is also, it's not. I think you're thinking of this. You're sort of thinking that the support should be in the test function space,
Right.
but no, it's actually in Euclidean space. So, so you get that, this goes to 0 in D, and so this thing goes to 0. So you can extend any compact that supports distribution is a temperate distribution. So this starts to give you some sense of what a temperate distribution is, right? It's a distribution with some sort of decay, right? You know, this is of course very, very serious decay, right? It vanishes. Not that at all, except, but let's go a little bit farther. So again, it's not really properties of temperate distributions, but just getting a sense of what temperate means. So let P be a measurable function, R, and such that for some P between 1 and infinity, and for some n greater than 0, we have the integral of g over 1 plus x squared to n to the p dx is less than infinity. So if there is some power of n, right? If there is some power of n, so that if we, divide g by the appropriate, this by this thing, and that thing we can make this finite, then g is a temperate distribution. So maybe it's not, I'm actually wrong to say, you might think that it's really a decay condition, but really it's not decay, it's rather slow growth, right? It's something about how fast you're growing, right? And actually, it's not, you could, right, so it's some sort of growth. Temperate distributions, it's a statement about how fast you're growing as you head off towards infinity. So in particular, any LP function any polynomial or measurable function whose absolute value is dominated by a polynomial is a temperate distribution. Okay. So this is, this should give you some more sense of what temperate distributions are. Let's prove it. Let S of G be defined as usual. Let Q be defined. Choose M such that the integral of 1 plus absolute value of x squared quantity to the n minus n cubed is finite. So choose some gigantic m. Necessary. As large as necessary. And we'll call this C, and then call this quantity B. Then observe. We consider F's F of we consider this. Well, by Holder's inequality, this is controlled by Qx 1 plus x squared and LP norm of that times the LQ norm of the other guy. Right? We're just multiplying, you divide this guy by this thing, and you multiply this guy by the same term. Got these two functions. Multiply one guy, divide by one term, multiply the other guy with the same term, right? You take the LQ norm of this guy, the LQ norm of that guy. You say, okay, well, we know that this term, right, this term here, bounded by that constant. And this term is bounded by b to the power q times the supremum of 1 plus x squared m f. That's the supremum over all. Do you see what I'm doing? So, do you see what we're doing? We slide in. Rewrite this as and minus n. Right, and then we have the. Slide in the term and we subtract out the term. Right? You take the supremum of this guy, you take the supremum of this, you pull it out. Right? This thing is controlled by this is dominated by the supremum, of course, right? So you can pull it out. right? And what you have left over is the B term. Okay, and so what you see then is that then if fn goes to 0 in S, right? If fn goes to 0 in S, well, that's going to imply that this goes to 0. Right? That this is going to go to 0. Right? What that implies is that fg at n goes to 0. G at n is controlled by these constants. Times this thing, right? But that's going to go to 0. So this goes to 0. Goes to 0. Right. But what that says is that this distribution respects the S convergence. So for the distribution satisfying this inequality, makes you into a temperate distribution. Because convergence in S to 0 means that this will go to 0. Because you know that the infinity norms of all polynomials times u is going to go to 0. So temperate distributions, right? Getting wider and wider. To further expand this, if A is any multi-index, P any polynomial, G any Schwartz function, then if F is a temperate distribution, then so are its derivatives. So is polynomial times the function, and so is the Schwartz class function times the distribution, right? Where these guys are defined as you have all these guys are still temperate distributions. And the reason is that the reason why is that all of these maps are all continuous linear maps, mappings of C of S into S. if you have convergence with respect, if you have convergence of the phi sub n to something, well then the, p times phi sub n are still going to converge to p times phi. Right? It's a continuous map. So it's still gonna, you still have continuity. So these are all, that's what that works. Okay, so maybe that's all I'm going to say about that's all I'm going to say about temperature distributions for now. Really the important thing about temperature distributions is the interaction with Fourier transform, which will allow us to do sort of great things. When I first learned about this, the professors said that in some sense distributions make things too easy for us. Like everything becomes possible. Okay, so let's see how let's see how this goes. Fourier transform. We're gonna talk about Fourier transform of temperate distributions. So just recall some facts. I've already recalled these facts before. So, so one, for phi in the Schwartz class, we have Fourier transform of phi. Fourier transform. Fourier transform is a continuous bijection in the Schwartz class into the Schwartz class, and it has an inverse, right? The inverse is the inverse Fourier transform, which we write with an upside down hat, where the upside down hat guy means you take you've seen it before. Okay. The relevant theorem for phi and c in the Schwartz class with multiplication identity. That is, you can pass the hat over to the other function. If you've got Schwartz class functions, you're integrating, c hat against phi. It's the same as the integral of c against phi hat. Okay, so that's just a reminder. About Fourier transform and distributions. So basically we take advantage of the niceness of the Schwartz class with respect to the Fourier transform. So given a temporary distribution, well, the Fourier transform, we define the Fourier transform of the temporary distribution in the obvious way, right? The Fourier transform will act, right? How are you going to do it? You know how you're going to do it. Right? Just look at this. Right? The Fourier transform is going to act on the function by integrating the original function against the Fourier transform of the test function. Right? It's written out here. Right? So you're going to just you're going to take you are going to take the original thing and act it on the Fourier transform. Right. If we write this in distribution language, right? The Fourier transform, the distribution corresponding to the Fourier transform ought to just take the function and then give you back what the original function's action on the Fourier transform function. The instructions are already there. Right? And the inverse Fourier transform, of course, will be defined in the analogous way. Okay. So, for example, if you have delta, the Dirac function, okay, and you have 1, we'll use the number 1 to denote the function, that 1 be the constant function 1. Okay. So the function that's 1 everywhere. Then, well, if you take the Dirac delta, I'm sorry, if you take the Fourier transform of the Dirac delta, what does that do? Well, the Fourier transform of the Dirac delta, by definition, ought to be the Dirac delta acting on the Fourier transform, right? Well, the Dirac delta acting on the Fourier transform ought to pick off the value at 0, right? Or pick off the value at 0, right? But what is that? That's the integral of phi. Right? The Fourier transform evaluated at 0, this term vanishes, and you get the integral. Right? Which you could think of as the integral of phi against the constant function 1. Right? In other words, it's 1. It's the constant function 1 as a distribution acting on phi. Okay. So the Fourier transform of the Dirac delta is 1. It's the constant function 1. Similarly, right, so it's a constant function. Similarly, right, if we took the constant function 1 and took its Fourier transform, well, that would be 1 acting on the Fourier transform of that guy. Well, that would be the integral of Fourier transform. Right? If you use the inversion formula, right, so you think sort of in a naive way, right? If you use the inversion formula, you see that this is phi of 0, right? Which is to say, the Dirac delta acting on phi, right, as a distribution, right? So, conversely, we see that the Fourier transform of 1 is the delta function. is also easy compared to everything, everything we did before. I don't know whether to feel relieved or sorry or relieved or apologetic. And it's so easy. Things will get harder soon enough if you're bored. Yeah, so, but not that. So, okay. So we, yeah. So it's something I should have said earlier. Okay. So, actually, I'll say that in a minute. Let me continue along in the same pleasant line of reasoning since it's easy. A bit further, that if you take the Fourier transform of a derivative, then as you might expect, you get the appropriate mononomial as the Fourier transform of the distribution. And this is just a calculation. It's in your book. I don't think it's worth talking about. And then we also have the converse. If you take the Fourier transform of the monomial of the appropriate monomial times f, well, you get the derivative of the Fourier transform. Okay, so that is, if you're familiar with how the Fourier transform behaves, Fourier transform still behaves the way that it did before. Right? That is, it takes differential operators and changes them into multiplications by polynomials and vice versa. Okay, and this is going to be the key thing, right? For when you take, because we'll use this to talk about to take differential equations and then change them into simpler things which we can solve. Okay, so in particular, if we let f be 1, right? If we let f be the constant function, this says that w by s alpha, the Fourier transform of that is going to be d alpha of the delta. And conversely, if we have d alpha x of the Dirac delta, right, then we're going to get these polynomials out. So it's easy to calculate Fourier transform of the partial derivatives of the Dirac delta. Their Fourier transforms are the monomials. So that's pretty So the last thing I want to mention is just a notion of convergence. If Fn and F are temporary distributions, then we say Fn converges to F in the sense of tempered distributions. Okay, so we have that is, we're putting a topology on the space of tempered distributions. Right? So this is putting it to converge in S star. One has a topology on S star. And it's easy to see that Fourier transform, or the inverse Fourier transform, continuous with respect to the relative sense of convergence. Obviously, actually. Obviously. Okay. That's actually all I prepared for today. I'm afraid I ran out of material. Sorry. Strange. Maybe you're relieved. Any questions? So what we'll be doing soon, if you've read ahead, one will be looking at the Hilbert transform as at the kernel of the Hilbert transform as a distribution. Two, we'll be looking at the solution of certain partial differential equations using what you might expect, the Fourier transform and distributions. And then three, we're going to look at a general definition of singular integral operator using something called a Calderon-Zygmunt distribution. And so that will be, those are generalizations of the Hilbert transform. The Hilbert transform is convolution against, something like 1/x, right? So we'll be talking about the general. It's not the. There are many ways of defining singular integral operators, and so this is just this is like one of the earlier definitions. But once we have it, it'll allow us to see a lot of the subtleties involved dealing with such operators. So that's look forward to it. It should be fun. That means it should be fun.